You don't usually see a rocket company trying to build the world's most ambitious microchip factory, but that is exactly what SpaceX is doing with Terafab, a multi-phase manufacturing complex planned for rural Texas. Modern aerospace vehicles like the Starship require an immense amount of localized computing power just to get off the launch pad. Back on the ground, the terrestrial endpoints of their global communications network require millions of custom receivers. Every single one of these physical systems is entirely dependent on the availability and design speed of specialized silicon wafers. By owning the fundamental hardware of computing, SpaceX removes the external constraints on how fast they can iterate and deploy their infrastructure in orbit. Right now, the semiconductor supply chain is fractured. A chip might be designed in California, fabricated in Taiwan, and packaged in Europe. That distance creates a logistical bottleneck. Moving wafers across functions introduces a multi-quarter delay between designing a chip and receiving finished hardware. SpaceX has a long track record of solving production delays by pulling external supply chains directly in-house. Relying on third-party foundries for their next generation of AI and space-hardened processors simply does not align with their aggressive launch schedules. To build a fully self-contained technological ecosystem, they have to absorb the entire semiconductor manufacturing process themselves. The official site for this project is Grimes County, Texas, backed by a $30 million state-level enterprise grant. The first phase alone requires an estimated $16.8 billion in capital investment and will bring in roughly 3,000 specialized workers. At 100 million square feet, the completed facility would stretch 2.5 miles. This footprint expands outward into modular phases. The stated goal is producing enough chips for 1 terawatt of AI computing capacity every single year. Terafab is designed as a modular industrial blueprint that can theoretically expand as fast as they can pour concrete. The core technical premise here is extreme vertical integration. They plan to put logic fabrication, memory production, and advanced packaging under one roof. In standard front-end processing, highly specialized machines extreme ultraviolet light and chemical etching to carve out nanometer-scale circuits on bare silicon. From there, the back-end process involves dicing those wafers, performing precision wire bonding to connect the circuits, and running extensive stress tests. By executing all of these steps in adjacent rooms, engineers can design a photomask, print a chip, test its performance, and immediately tweak the design based on the results. This total physical consolidation turns a slow, rigid hardware supply chain into a rapid iteration loop that feels much closer to software development. All of this terrestrial manufacturing is built to serve a specific environment, an orbital AI network known as StarMind. To operate in space, these chips must be rigorously hardened. They require extreme physical precision to survive high orbital radiation and brutal thermal fluctuations. The StarMind architecture involves placing AI data centers into sun-synchronous orbit, allowing the satellites to capture continuous, direct solar power without any weather or atmospheric interference. This location also solves one of the biggest bottlenecks for terrestrial data centers: heat. Instead of consuming millions of gallons of water for cooling towers, the satellites radiate excess heat directly into the freezing vacuum of space. Once processing is done, the satellites transmit AI results back to Earth using high-bandwidth, low-latency laser links tied directly into the existing Starlink network. The two concepts are completely codependent. The massive factory in Texas is the intended engine required to physically build this orbital infrastructure. But moving from ambitious blueprints to operational foundries involves navigating a maze of severe industrial hurdles. A semiconductor plant of this scale demands vast environmental resources. It requires tapping a nearby reservoir for intensive water usage, building dedicated on-site wastewater treatment, and constructing standalone natural gas power plants just to keep the lights on. Then there is the human capital constraint. Operating these cleanrooms means convincing thousands of highly specialized semiconductor technicians to relocate to a largely rural county. Furthermore, the first phase of Terafab is built around Intel's 14A process technology. This confirms that even with massive capital, they cannot simply invent every step of modern chip fabrication from scratch. Infinite funding and aggressive timelines cannot instantly bypass the hard physics and established supply limits of the global semiconductor market. At its core, the Terafab project serves as a unifying foundation for Tesla, SpaceX, and XAI. The plant has a strict dual focus, churning out inference chips to power terrestrial robots and self-driving vehicles, alongside the hardened processors needed for their orbital data centers. If this Texas facility fails to achieve viable manufacturing yields, the company's entire schedule for scaling up AI and expanding into space will stall. Terafab represents a massive test of vertical integration, an effort to control the entire technological chain from the Texas soil to high-performance compute modules in low Earth orbit.